So in the last video, we talked about how to find the Laplace transform of some function. I bet you've been wondering, well, if I can go into Laplace world, there's got to be a way to get out of Laplace world. And there is. We're going to discover that today. And that is called taking the inverse Laplace. So we're going to look at inverse transforms. And a lot of this really has to do with just kind of matching up with our formula sheet, looking at the table of Laplace transforms. So let's take a look at a few. So we derived a few of these last time. We actually derived that one and that one and that one. So if we wanted to take the Laplace of 1, when we applied the Laplace definition, which, if you recall, taking the Laplace of f of t requires an integration, integrating from 0 to infinity of e to the negative st times f of t dt. And when we did that for 1, we ended up with 1 over s. So if we wanted to get back to 1, remember this function is going to live in our regular rectangular plane. This is the Laplace transform. We could take the inverse Laplace of 1 over s, and we're going to get back to that 1. So likewise, when we found the Laplace of t, we applied that formula, and we ended up with 1 over s squared. So if we wanted to get back, let's say we started in a Laplace world, and we want to go back to rectangular world, then we can apply the inverse Laplace of 1 over s squared, and that will give us t. When we derived this one, we plugged everything into our formula to integrate. And when we integrated, we ended up with 1 over s cubed. So to find the inverse Laplace of this, we could think about rewriting this as s minus negative 3. And we are taking the inverse Laplace. And that's going to get us back to e to that negative 3t. So everything's really coming from that formula sheet. Because remember, that's the shortcut rules that have been derived for us without us having to go through that long process of integration. It's really similar to those derivative rules that you did back in Calc 1. In Calc 1, you found derivatives by hand using the limit process, and then we said that there were some shortcut rules that we could use. So we no longer use that limit process to find derivatives. These rules are really similar to that. This table has been derived for us. So now sometimes if we're trying to get back to that original function, it may take a little tweaking to get us there. A good example is actually this last one, finding the inverse Laplace of 1 over s plus 3. We want to match it up with this formula if we possibly can. So we really need to figure out what our a is going to be. So we could rewrite that s plus 3 as s minus negative 3. And now we're written in that form where we know what a is going to be. So then we know what that exponent on e is going to be. So this is just a few of those inverse transforms. We can actually get the same kind of ideas from our Laplace table of transforms. So you just have to think about what is this side, and then what do I need to do to get this guy back. So if we were to take the inverse Laplace of 1 over s squared, we're going to get t. So we're reading that table backwards instead of left to right to go into Laplace world. We're now reading it right to left to get out of Laplace world. So there's our exponential one there that we talked about. So we have 1 over s minus a. If we want to take the inverse of this, we will get e to the at back. So you can see how that table is working. So I want to play with this and look at a few examples. So keep in mind, like we said just a few minutes ago, we may have to tweak or fix up this function by doing some fancy math to help us do that. And we're going to see that in just a few examples. So let's look at these. We want to look at the inverse Laplace of 1 over s to the 5th. So if we go back to our sheet, and I'm going to use just this page over here, we're trying to fit this guy because we have some number over s to the n plus 1. So let's write down what we know so we can see how we're going to tweak this. So if we were to rewrite this guy, we could rewrite as s to the 4 plus 1, and that has written that exponent on s in a way that matches what our formula is for that inverse Laplace. But we're missing that n factorial here. So what if we were to change this so that we have a 4 factorial here? Now, if we multiply by 4 factorial, we also have to divide by 4 factorial. That way we're really just multiplying by 1, and it's not going to change the problem. And because this 1 over 4 factorial isn't going to be affected by this inverse Laplace, remember this is a linear transformation, then we could factor it out. So now we have 1 over 4 factorial times the inverse Laplace of 4 factorial over s to the 4 plus 1. So 4 factorial is the same thing. Remember, factorials can be written as 4 times 3 times 2 times 1. And that's going to be 24. So it's 1 over 24. This guy is going to translate to t to the 4th. So that was our original. So there's our f of t. So if you wanted to check it, you could always find the Laplace of that. It may take some work. If you're doing it by hand, you could also use your formulas. So finding the Laplace of t to the 4th over 24, that should give us our 1 over s to the 5th there. Just by applying the formulas to that, or doing integration if you wanted to do that. That would take a few by parts. Let's look at B. We want to find the inverse Laplace of 1 over s squared plus 7. So if we're thinking about our formulas, and I'm actually going to go to that formula sheet so you can see how that's going to work. We have a number over s squared plus a number. So we're trying to tweak it in terms of this sign here. So it's going to end up being some kind of sine function. We just got to figure out how to tweak this side over here. That k over s squared plus k squared. So here's what we know. Going from that formula sheet, if we were to take the inverse Laplace of k over s squared plus k squared, then we would end up with the sine of kt. We just have to do some tweaking to get us there, because right now we're missing a number in the numerator. So let's tweak. Now we could rewrite 7 as the square root of 7 quantity squared. So that gives us our k squared. So now we know k has to be square root of 7. But we're still missing that square root of 7 in the top. So we can multiply the top by square root of 7 as long as we also multiply the bottom by square root of 7. Now, that bottom, that square root of 7 there, we can pull that out. That's 1 over square root of 7 times the inverse Laplace of the square root of 7 over s squared plus square root of 7 quantity squared. And now this guy fits the formula that we need. And this is going to be 1 over square root of 7 times the sine of square root of 7t. So there's our f of t. So you can see how we're using those formulas to help us do that. And you can also see how we're having to tweak some of these just a little bit. The inverse Laplace is a linear transformation. So all those linear transformation properties still apply. We can split this up into the sum of two inverse Laplaces and factor that constant term out. So I want to do a few more of these. Let's look at example 2. Now we've got a lot going on here, and there's not a formula that's going to quite match this. So let's use those transformation properties and rewrite this. We're going to split that numerator and see if that's going to help us make things a little bit easier for us. And then we could also pull this negative 2 out of the first piece and pull the 6 out of the second piece. So let's go back to our formula sheet and see if we have something that looks like this and looks like this. And I'm going to use that standard formula sheet just because it has more options than what was in that theorem. The theorem was just a small selection of things. So we had an s over s squared plus 4. So that's going to match this number 8. So that's going to end up being a cosine. And then we had a 1 over s squared plus 4, which looks like we can tweak this sign to help us get there. So let's write down what we know over here. We know that if we were to take the inverse Laplace of k over s squared plus k squared, then it's going to be equal to the sine of kt. And if we take the inverse Laplace of s over s squared plus k squared, then that's going to be equal to cosine of kt. So let's try to rewrite these. We can rewrite that denominator for the first one as s squared plus 2 squared. So now we know what k is going to be. And then we can rewrite the denominator for the second one also as s squared plus 2 squared. So in that first one matches that cosine formula exactly. So this is going to translate to 2 cosine of 2t. But the second one needs a little bit more of a tweak. Notice to fit that sine formula, you got to have k in the numerator. Our k is 2. So we can multiply that in as long as we compensate for that 2 that we're multiplying in by multiplying by 1/2 somewhere. So now that piece is going to translate to 3 times the inverse Laplace of the sine of 2t. So there's our final answer. Don't forget the negative on the 2. We got a negative 2 to begin with. So there's our f of t function. If we were to check it, if we wanted to, we could take the inverse, we would take the Laplace of this. And then once we combine like terms, we would get this guy back. So it's just a way to kind of double check your work if you wanted to. Let's do another one. So we have this guy. Anytime you have multiple things in the numerator or multiple things in the denominator, see if you can break the numerator apart. In this case, we'll be able to use partial fraction decomposition because we have 3 terms multiplied together. So we want to simplify as much as we can and then try to compare with the formula to see if there's something that we could use. So let's simplify what we're trying to take the inverse Laplace of. So we're going to have a over s minus 1 plus b over s minus 2 plus c over s plus 4. So if we set up our partial fraction decomposition, we could multiply everything by that least common denominator, which is the s minus 1 times s minus 2 times s plus 4. That's going to leave us with the numerator, s squared plus 6s plus 9. That's going to be equal to a times s minus 2 times s plus 4 plus b times s minus 1 times s plus 4 plus c times s minus 1 times s minus 2. So I'm going to FOIL everything out on the right hand side. So this is s squared. 4s minus 2s is a positive 2s minus 8 plus b times s squared. 4s minus s is a 3s minus 4 plus c times s squared minus 3s plus 2. So let's compare numerators on the left and on the right. If we're looking at the s squared coefficients, not numerators, coefficients, excuse me. On the left-hand side, we have a 1s squared. On the right-hand side, if we were to distribute, we would have a plus b plus c. If we compare coefficients of s on the left and on the right, on the left we have a 6. On the right, if we were to distribute, we would have a 2a plus 3b minus 3c. And then if we look at constants on the left and on the right, on the left we have a 9. If we were to distribute, we would have a negative 8a minus 4b plus 2c coming from there. So this needs to go into your calculator to do RREF. That's the easiest way to solve. And when we do that, we will get the identity on the left. There will always be a unique solution for these. And I got negative 16 over 5 for A, 25 over 6 for B, and 1 over 30 for C. So we're trying to take the inverse Laplace of, and we're just substituting these numbers into this guy. So it's going to be negative 16 over 5 over s minus 1 plus 25 over 6 times s minus 2 plus 1 over 30 over s plus 4. So we can rewrite that. We can take the inverse Laplace of each piece. And then we can pull those constants out. And that will help us see how we need to tweak. If we need to tweak. So now we need to compare to our formula sheet. So I'm going to go back to that main formula sheet. And I'm looking for something that looks like 1 over s plus a number or s minus a number. And if we look at row 11, we see we have 1 over s minus a. And the Laplace of that, the inverse Laplace of this would be e to the at. So let's write what we know off to the side. This is coming from row 11. If we were to take the inverse Laplace of 1 over s minus a, that's going to be equal to e to the at. We just have to figure out what a is going to be. So in that first case, our a is going to be 1. In the second term, a is going to be 2. In the third one, we're going to have to rewrite this, so we really need to think about this as s minus negative 4. And that tells us a is going to be negative 4. Remember, it's the number after the minus sign. So let's write our final answer. So we're going to have negative 16 over 5 e to the t plus 25 over 6 e to the 2t plus 1 over 30 e to the negative 4t. So there's our f of t function. That's the inverse Laplace of what we started with up here. So there's our final answer.